You are all welcome to my online class. We'll be looking at Mathematical Methods 1, Lesson 1. Let's recall that in our past lectures, we have looked at the concept of differentiation and integration. So moving forward, we are going to look at advanced approach to differentiation and integration. Now, we are already familiar with the fact that differentiating a constant gives us 0. We also know the rules in differentiation, such as the chain rule, the product rule, the quotient rule, and so on and so forth. Now, let's look at some specific derivatives. We're already familiar with these derivatives. For example, the differentiation of x raised to power n is equal to n x raised to power n minus 1. The differentiation of natural logarithm of x is equal to 1 over x. The differentiation of sine x will give us cos x, while the differentiation of cos x will give us minus sine x. Now, this basic differentiation continues. These are basic terms we'll be coming across in the course of this course. So when you come across them, you should know how to use them. That is why we decided to state them earlier before we begin the lecture proper. Okay, now let's take some worked examples. Differentiate the natural logarithm to base e of the quotient square root of 1 plus s squared all over square root of 1 minus s squared with respect to x. Now, in trying to handle this problem, we know the basic relationship in logarithm. When you have a quotient, it is the same or equal to when you subtract the denominator from the numerator. And when you have a product in logarithm, it is the same as addition. So this is what we have done here specifically by separating them. Then by the time you separate them into components, you now differentiate each of the components and bring them together. Now, these are basically the steps. What you're seeing here is the proper differentiation of each of those terms component-wise. And after differentiating, you now start simplifying. And that is what we have done here. And our final result is 2x over 1 minus x raised to the power 4. So let's look at another worked example. If y equal to arc sine 1 plus 2 sine x all over 2 plus sine x, find y prime. This is another example, and I'm sure we didn't do this in the class, so this will give you an opportunity to review what we are doing. Some of the assignments I've given to you, this will also give you an opportunity to look at them all over again and try to find solutions to them. Now, in this particular problem, we said I let you be everything in bracket, which is 1 plus 2 sine x all over 2 plus sine x. Then you write your y to now be arc sine u. And what this means is that you're going to do two things here. You're going to differentiate y with respect to u and differentiate u with respect to x, and you take their product. This is what we call the chain rule. And when you do that properly, this is what you're going to get. And the final solution here will be 3 cos x all over 2 plus sine x all squared. Therefore, you continue the simplification, and you can see how lengthy the simplification is. By the time you substitute back your u and you continue the simplification, you're going to have 3 cos x all over 2 plus sine x times 1 over the square root of 4 plus 4 sine x plus sine x squared x minus 1 minus 4x minus 4 sine square x. And when you continue the simplification all over again, knowing that 1 minus s squared will give us cos s squared, you substitute back, and at the end we are going to have that the derivative of that question will give us square root of x all over 2 plus sine x. Let's look at more examples. If y is equal to arctan log of x, find y prime. Solution. To find y prime is the same as finding dy dx. Okay, and this one is easy because the function is already in x. So when we already know that differentiating log x will give us 1 over x, and we have all this now. By the time you simplify, you get this as the final answer. Let's look at more worked examples. If y is equal to arctan 2x over 1 minus s squared, find dy dx. I want you to know that the reason why we are doing these online lectures is because in the class we are time bound. There's no way we'll be able to complete all these things right in the class. So we need to take some time online to do some of these things, and when we meet physically, we can explain better. So in this kind of problem, what you're supposed to do is to say let x be tan theta. If x is tan theta, then tan 2 theta is also this. These are trig identities. Hence, writing the original question will now be that y is arctan 2 tan theta all over 1 minus tan theta squared, because x is tan theta and s squared will be tan theta squared. So by the time you open up y, you would have now that y is equal to 2 theta, and dy d theta will give us 2. Similarly, dx d theta, because you remember we have x equal to tan theta, so dx d theta will give us secant square theta. But secant square theta is the same thing as 1 plus tan square theta. You replace it, and when you take their product, you are now going to have that 2 times 1 over 1 plus tan square theta. Okay, now we are going to go back to the original question because x equal to tan theta is an assumption. Our problem is actually in x and not in theta. So when you go back, you will now have that dy dx will now be 2 times 1 over 1 plus s squared, and this is the final answer. Now let's look at more examples. If y is equal to arc cos 1 minus s squared all over 1 plus s squared, find dy dx. Solution. Let x equal to tan theta, then y is equal to arc cos 1 minus tan square theta all over 1 plus tan square theta. And this implies that y is equal to arc cos 2 theta, and simplifying will give us 2 theta. The reason why we're always doing this is that it helps us to easily carry out the differentiation. Now at this point, the y d theta is just 2, and the x d theta is 1 plus tan square theta, which will give us 1 plus s squared. Now reversing back to the original problem, which is in x and not in theta, you will now have that dy dx is 2 times 1 over 1 plus s squared, which is equal to 2 all over 1 plus s squared. Let's look at more worked examples. Now, if y is equal to x square root of s squared plus 1 plus the log in bracket x plus square root of x squared plus 1, find dy dx. Now, solution. This is simple. You say let y be the question given. Then dy dx is simple. We are going to differentiate component by component with respect to x, and this is what you're going to get. Now when you start simplifying all these things, you now arrive at 2 square root of x squared plus 1. You see, and this is our final answer. after proper simplification. Now, it's time to start differentiating implicitly with respect to x. Let's look at some examples. If x and y is equal to a exponential raised to power x plus b exponential raised to power x plus x squared, show that x d 2y over dx squared plus 2 dy dx plus x squared minus xy equal to 2. In this case, you're going to say proof because you're asked to show. So in the proof, what we're basically going to do is you're going to differentiate y twice here, then multiply by x. In this component, you differentiate y with respect to x and multiply by 2. And at the end, we'll see if when we add x squared minus xy, we are going to have 2. So this is what we are going to do here. So differentiating your xy with respect to x will give us this. And when you continue, therefore, you're going to, when you differentiate again twice, you're going to have dy dx plus x dy the squared y over dx squared plus dy dx, which is this. Okay, now therefore multiplying x to this and y to dy dx will now give us this. But a exponential raised to power x plus b exponential raised to power x is equal to xy minus x squared. Therefore, you now replace this thing here with this, and this is how we arrive at this plus 2, and this is the final show of proof, because when xy moves over to the left hand side and minus x squared move over to the left hand side, then we are going to have the original question which they asked us to show. Therefore, this is the final answer as stated earlier. Let's look at another worked example. If x squared y is equal to cos x, show that x squared the square y over dx squared plus 4x dy dx plus 2 plus x squared y equal to 0. Proof. Let x squared y equal to cos x, which is given. Then differentiating the first time, you're going to have this, and differentiating again the second time, you're going to have this. But cos x is equal to x squared y, so substitute, you're going to have what we have on the board. Then when you simplify, you get back the original question. Therefore, x squared the square y over dx squared plus 4x dy dx plus y in bracket 2 plus x squared is equal to 0, and we have shown that. This is another worked example, that if y is equal to x plus square root of 1 plus x squared raised to power p, show that 1 plus x squared the square y dx squared plus x dy dx minus p squared y is equal to 0. Proof. In proving, we say let y equal to x plus square root of 1 plus x squared raised to power p as given. Now we are going to differentiate once dy dx, you have this. Okay, and when you simplify that dy dx further, you have this. Now you continue and differentiate twice, then you have this. And when you simplify further, then you're going to have this final result here, which is square root of 1 plus x squared dy dx is equal to p in bracket x plus square root of 1 plus x squared raised to power p. But square root of 1 plus x squared dy dx is equal to p y from our initial assumption. So continuing, you do your substitutions, and when you simplify after your substitutions, you're going to have that x dy dx plus 1 plus x squared the square y over dx squared will be equal to p squared y. And when the p squared y crosses over to the left hand side, you have it to be equal to 0. So let's look at some differentiation of parametric functions. Recall that if x and y are expanded in terms of a third variable theta or t, then the third variable is called a parameter, and the equation containing a parameter is known as the parametric equation. Now, if x is equal to ft and y is equal to gt, then dy dx is equal to dy dt divided by dx dt, depending on the parameter that was used. And this will give us dy dt times dt dx. And differentiating twice will give us the square y over dx squared will be d dt dy dx all over dx dt divided by dx dt. Now let's look at some worked examples. If x is equal to cos 2 theta and y is equal to 2 theta minus sin 2 theta, find dy dx and find the square y dx squared. So find the first derivative and the second derivative of the functions x and y. So this is easy to do. Under solution, you say let x be 2 theta and let y be 2 theta minus sin 2 theta as given. Then dx d theta will give us this, y dy d theta will give us 2 minus 2 cos theta. And when you now join to get your dy dx, will now give us dy d theta times d theta dx. And when you simplify through, you're going to get minus tan theta as your dy dx. Similarly, the second question, which is find the second derivative, you now differentiate again the first derivative twice, and this is what you're going to get, and the final answer will be sec cube theta cosec theta all over 4. The reason being that some trig functions here will play a role in this denominator. We all know the trig ratios of sin 2 theta, and when you put that here, it will come here and become 4 sin square sin theta cos theta. Okay, so sin 2 theta, you know the trig ratio or the trig identity, then you multiply it by 2, you actually get this, because sin 2 theta is 2 sin theta cos theta. Multiplying it by 2 gives us 4 here, and this is how we got the 4. Okay, all right. So this is your final answer. Okay. Let's look at some more worked examples. If x is equal to a in bracket t sin t plus cos t minus 1 and y is equal to a sin t minus t cos t, find dy dx and the second derivative. Find the first and second derivative. Solution: let x be equal to a t sin t plus cos t minus 1. Then the x, the y will be a sin t plus t cos t minus sin t. And similarly, if y is a sin t minus t cos t, then the y dt will give us a cos t minus cos t plus t sin t. Okay. So hence, dy dx will be dy dt times dt dx. And when you do that properly, you're going to have tan t. And the second derivative here will give us sec cube t all over 80. Let's look at a successive differentiation. If y is equal to f of x, its derivative dy dx is also a function of x. Dy dx is further differentiated, and the derivative of y, that is d dx of dy dx, is called the second derivative of y and is denoted by d squared y all over dx squared. Similarly, the third derivative of y with respect to x is written by, yes, the third derivative d3y over dx3. Thus, dn dy all over dxn is the earning derivative of y with respect to x. Note that we can use any of the notations as stated here to denote the earning derivative of y with respect to x as well. So let's look at some worked examples here. To find the 24th derivative of the function y equal to x raised to power 31. Solution. Let y equal to x raised to power 31. Then y prime, the first derivative, will give us 31x raised to power 30. Y prime prime will give us 31 times 30 raised to power times x raised to power 29. While the third derivative will give us 31 times 30 times 29 x raised to power 28. Now, continuing this, you are going to discover a pattern or a sequence. Okay, and that sequence will give us 31 factorial all over 31 minus n factorial x raised to power 31 minus n. Thus, y raised to power 24 will be equal to 31 factorial all over 31 minus 24. So anywhere you have n, you replace it with 24, and this is what you're going to get. So our final answer here will be 31 factorial over 7 factorial x raised to power of 7. Let's look at another worked example. Find the earning derivative of the function y equal to 1 over x minus 1 raised to power 3. Solution. Let y be this. So you write y and you have this. Then you look for the first derivative, second derivative, and the third derivative. You will discover that when you continue, you're going to see the pattern to be y raised to power n will be equal to minus 1 raised to power n plus 2 factorial over 2 factorial x minus 1 raised to power minus n plus 3. So this becomes the general term of the sequence. With this general term, you can actually find any term of the derivative. So if you're asked to find the 15th derivative of this problem, you simply replace n with 15. If you're asked to find the 10th derivative, anywhere you see n, you represent it with the number that you are asked to differentiate. So that is the way it is. Let's look at another worked example. To find the nth derivative of the function y equal to 1 over x minus 1 in bracket x plus 2 in bracket all squared. Solution. I believe we have done this in the class. We resolve into partial fractions and differentiate separately. So this is what you have, and in using the method of partial fraction, you're going to find your a, your b, and your c. And how do we find our a? You say let x be equal to 1. Your a will now be 1 over 9. Similarly, how do we find c? You say let x be equal to minus 2, and c becomes minus 1 over 3. Now we have gotten a, we have gotten c. The next is to get b. You simply substitute you now say the relation when x is 0, you have 1 equal to 4a minus 2b minus c. Now substituting your a and your c and make b the subject, you're going to get that your b is equal to minus 1 over 9. Now going back to the original question, you will now have that y is equal to 1 over 9 x minus 1 raised to power minus 1 over 9 x plus 2 raised to power minus 1 over 3 x plus 2 raised to power minus 2. At this point, you can now differentiate the y dx component wise. Each of them will be differentiated separately. So you take the first derivative, second derivative, third derivative, then you look out for a pattern that you can follow, and then the pattern will now be that y raised to power n will be equal to minus 1 raised to power n over n factorial x minus 1 raised to power of minus n plus 1 minus 1 over n times minus 1 raised to power n factorial. x plus 2 raised to the power minus n plus 1 minus then minus 1 raised to the power n over 3 times n plus 1 factorial x plus 2 all raised to the power minus n plus 2. So this is the general nth term of the derivative. This is what we mean by successive differentiation. Let's look at another worked example. If y is equal to sine x, find the nth derivative of y equal to sine x. Now in trying to find the solution, you say let y be equal to sine x as given. Then we already know what cos x is because trig functions are actually periodic. So by being periodic, we mean that you can actually find the relationship between cos x and sine x. So cos x is equal to sine x plus pi over 2. We look at the first derivative. If y is equal to sine x, y prime is equal to cos x, and that will give us, being periodic, will give us that sine x plus, we'll replace x cos x to be sine x plus pi over 2. The second derivative will give us cosine, but we'll change it again to sine using the periodic component, and we now have sine x plus pi. The third derivative, the same thing, and we discover that there is a pattern here. The reason for doing this is that we want to create a pattern which we can use to generate the nth derivative, and this is what we now have. Continuing, we discover that y, the nth derivative, will be equal to sine x plus n over 2 pi. In summary, we have completed the following topics: review of differentiation, parametric differentiation, implicit differentiation, and successive differentiation. So in our lesson 2, we are going to continue with Leibniz theorem, Taylor's and Maclaurin, and so on and so forth. Thank you so much for listening. Bye.